You understand the principles of the bearing capacity, right? Repeat.
So we're actually a passive zone, sir.
Oh, I was actually up here.
Yeah, you were explaining the passive zone to us.
Oh, all right. So when we talk about passive pressures, we have is actually deal with lateral or pressures, right? So we have pressure acting laterally. It's the horizontal component of a vertical stress that is acting on a soil particle. Good. And there's a reaction from a soil particle actually to push back against that force. So that's our passive force. We have three types of lateral pressures acting on walls, right? For those that have not done geotechnical engineering as yet, we have passive, we have active, and we have lateral. Sorry, we have at rest earth pressures, right? When we deal with foundation soils like these, for the most part, what we have is passive zones or passive pressures that are acting within your soil. Good. So based on that, we have Tarsaga has developed what is called the general bearing capacity equation, right? And this equation varies for strip or continuous foundation, for circular foundations, and for pad footing, right? So it's generally used for three different types of shallow foundations. Good deep foundations are analyzed in different ways, which we'll do later in the module. So for a strip or continuous foundation, and a strip foundation is something that is a function that you see every day and domestic housing. Good. Where we have a continuous foundation that is which the walls, the structural walls actually rest on. All right. So we have QU, which is the ultimate bearing capacity of the foundation. That's QU. Good. Um, is equal to C prime NC plus Q NQ plus half gamma B N um gamma. All right. So so C prime is actually the soil's cohesion, right? And it's measured in kilonewtons per meter squared. We have NC, which is our bearing capacity factor with respect to the soil's cohesion, that can be calculated or read from a table based on the soil's friction angle. Good. So all of these bearing capacity factors is actually a function of the soil's friction angle, right? Then we have Q and Q, right, which is the stress or the overburden pressure acting on the soil at the bottom of the foundation, which is equal to the unit weight of the soil times the depth of the foundation. Good. And times or bearing capacity factor with respect to the stress actor soil. Then we have half gamma, which is the size unit weight, times B, which is the breadth of the foundation, times N gamma, which is our bearing capacity factor with respect to the size unit weight, and also a function of the soil's angle of friction. Good. We have And all these bearing capacity factors can be calculated or they can be read and from a table. Good. But either way, we must determine the size friction angle in order to determine these bearing capacity factor. All right, so the ultimate bearing capacity of a soil then based on this equation um has three different areas or three right? um Three terms that contributes to the overall bearing capacity of a soil. The first that contributes the first term and the soil's cohesion, right? The second term gives this contribution from the stress and the overburden stress already developed in the soil. And the third is based on the soil's unit weight. Good? So, as I was saying earlier, if the soil bearing, if when we calculate, we get a bearing capacity, a ultimate bearing capacity QU of say 50 kilonewtons per meter squared, right? When we calculate the load acting from our structure, right, we have 100 kilonewtons per meter squared. Then we know that our soil is going to fail. We're going to have shear failure occurring in our soil because the ultimate bearing capacity is less than the load that is being applied from the structure to the soil, right? In that case, there are a number of things that can be done. One, we can modify our design and increase B, which is better for our foundation, right? And by increasing B, we are going to also be increasing our ultimate bearing capacity, right? That's one. The next we can actually change the type of foundation, for instance. So if we are exceeding our ultimate bearing capacity um, by say 2 or 3 times, um, what we need to do maybe is to say design a raft foundation instead of a strip foundation because the raft, the strip foundation becomes so wide, right? And we increase B in some cases, that it takes up more than say 2/3 of the entire floor area. And in that case, instead of making a wide strip, we just make a raft foundation. Um, Good. And so the distribution of loading on the soil becomes much less. Are we okay? Are we good, guys? All right. Um. So I know we are talking about bearing capacity. There's much more to function design, which we'll see later on, right? But just well, take it bit by bit. All right. So we are at the bearing capacity factors. NC, NQ, and N gamma are defined by. So we have NC is equal to, again, we need to know the fire size friction angle is equal to the cut. I'll just go to the reduced format, the cut of um, our phi angle, which is the internal angle of friction for the soil, um, times NQ minus 1. And NQ can be calculated as NQ is equal to E to the 2 times 3 pi over 4 minus our side friction angle over 2 times tan of phi divided by 2 cos squared 45 plus phi over 2, and we have n gamma is equal to half of kpy divided by the cos square of our phi angle minus 1 um, times the tan of our phi angle, right? Where kpy is a passive pressure coefficient, right? Remember when we do lateral pressure, we have Rankine's coefficient of passive pressure. Good. So that would that be that? So that the passive pressure of coefficient tells us what fraction of that vertical load actually acts laterally. All right.
So could you repeat that please again?
Right. I'm saying that the passive pressure coefficient will give us an indication of what fraction of the vertical load that is applied from our structure actually also act laterally below the foundation and will result in failure. Okay. All right. For then we have we have as I said before that we have this type of foundation is Rankine theory. I'm sorry, tertiary theory actually is actually used for three different types of foundation: continuous or strip, square foundation, and circular foundation. Right? The formula I gave earlier applies only, remember, applies only to continuous and strip foundations, right? For square foundations, say like a pad, it is actually 1.3 times our coefficient, um, our 1.3 times our size cohesion times our bearing capacity factor NC plus Q. And again, Q is, anybody remember what Q is again? What's Q?
The, the load,
Load.
the total load, sir.
How you calculate Q?
The
There
factor
isn't
combination.
isn't two of the dead and live load being imposed on the foundation.
Not in this case.
Oh.
This Q is the stress acting at the bottom of the foundation from the soil, the imposed load from the soil above the bottom of the foundation. And this Q is equal to gamma times the depth of the foundation. So it's a unit weight of the soil times the depth of the foundation that gives you Q. Okay? When we are doing bearing capacity, that's what it represents. Okay?
All right, sir.
Big Q, which we will see, our capital Q, which we'll go to later on, will have to do with the imposed loads. Okay?
Sir, can you repeat what SQ is again?
It's actually the stress acting at the bottom of the foundation from the soil, the overburden pressure from the soil itself, right? So it's actually the unit weight of the soil times the depth of the foundation. Right? So it's measured in kilonewtons per meter squared. Good. So it's unit weight, which is kilonewtons per meter cube, times the depth in meters of the foundation. Okay? We clear with that, guys? Everybody? Are we clear?
Yes, sir.
All right. 0.4 plus 0.4 times gamma, which is unit of the soil, times B, which is the breadth of the foundation, right? And times N gamma. Good. And for circular foundation, it's 1.3 times the soil's cohesion times NC plus QNQ plus 0.3 gamma times BN gamma. Good. All right. So all right, let me go back here a little bit.
Sir, are these formulas that we're supposed to know off the top of our head, or they'll be formulas that will be given?
Like this formula will be given, right?
Okay.
For these are normally read from tables. All right. If you don't find them, you can calculate it, but it's normally read from tables, and this is one such table. All right. So once I know the shear angle, the internal angle of friction for the soil, that's phi, right? I say phi is 30, 35, which is common. Then I can go ahead and read all of these bearing capacity factor. Good. So it's
Yes, sir.
30. I could go ahead and read all the bearing capacity factors. And really you don't know need to normally you don't need to go back and calculate all of these. Okay? They're already in design tables for you. All right, so we have modification for local shear failure. For a foundation that exhibit the local shear failure mode in soils, Tarsages suggested the following modifications. So these are the modifications to the different type of foundation. So if you are working, say for instance, in a medium dense soil, right? I show you a table earlier that gives you the relative density and BF over B, right, for the soil. So if based on that graph, you can actually determine what type of failure are expected to encounter within your soil. Good. Based on that, you can know if you must use the modified bearing capacity equation or you're going to use the general form. Understood? Let me go back to the graph, just in case somebody had missed it. So if you know the relative density of your soil, say it was 0.5. Good? For the relative density of the soil, right? You know that you are in somewhere within the local shear failure zone, and you'd really want to use that for the modified form of the bearing capacity equation. Where am I? All right, so these don't need to go through these one by one. This is just a modification of the base of the bearing capacity equation based on designing in a soil that will most likely or not experience local shear failure if failure should occur. All right. So these are bearing capacity factors. Good. All right, factor of safety. All right, calculating the gross allowable load bearing capacity of shallow foundation required the application of a factor of safety to the gross ultimate bearing capacity. Our QR is equal to QU divided by FS, right? So we'll have normally a bearing capacity ranging from normally between 2 and 3, but can be between 1.5 and 3. Some foundation goes up to 4 based on the type of situation and uncertainties that we are working with, right? So it's our ultimate, our allowable load carrying capacity of the soil is equal to our ultimate bearing capacity is divided by our factor of safety, right? And as the engineer, you are going to choose a suitable um, factor of safety. However, some practicing engineers prefer to use a factor of safety such that the net stress increase on soil is equal to the net ultimate bearing capacity divided by your factor of safety, right? So we know to calculate our net ultimate bearing capacity, right? You calculate that just now. The net stress increase in the soil um, is based on the imposed load, right? Remember, we have stressed already in the soil based on the overburden pressure of the soil itself, which would have calculated in soils class, right? And a little geotechnical. Now, when we add a structure and when we add an imposed load, right, there's an net increase in stress in that soil that can be calculated based on the load that is added, right? So we're saying that the net stress increase and the soil is equal to the ultimate load bearing capacity um, divided by your factor of safety. And that will give you a minimum factor of safety. All right. Q net, or net ultimate bearing capacity, is equal to um, QU minus Q. Q Q net is equal to our net ultimate bearing capacity. Q is equal to again gamma DF, and QR net is equal to QU minus Q over FS. That's our ultimate bearing capacity, or allowable bearing capacity, right? So although we know the soil is able to carry um, 90 kilonewtons per meter squared, right? We might use a factor of safety of say 3, and from that we know that we are able to carry 30. We are going to design for no more than 30 kilonewtons per meter square for our soil. All right, so a square foundation is 2 meters by 2 meters in plan. The soil supporting the foundation has a friction angle of phi equal 25 degrees, and C prime equals 20 kilonewtons per meter squared. So the side friction angle is 25 degrees, and um, our soil's cohesion is equal to 20 kilonewtons per meter squared, right? I know that we didn't have the shear machine um, working, up and working. So many of you at the geotechnical were not able to actually determine the shear angle of a soil for yourself. But I can still try to have you do it this semester when we do our field trip. Okay. All right. So the unit weight of the soil gamma is 16.5 kilonewtons per meter cube. Determine the allowable gross load on the foundation with a factor of safety of 3, assuming that the depth of the foundation is 1.5 meters, and the general shear failure occurs in the soil. All right. So we have a square foundation, square, right. All right, there are things that we determined. As a practicing engineer, right? I'm going to be determining this, the depth that I'm going to place my foundation at, right? And this is going to be based on my geotechnical data. When so I'm going to look at my soil profile from my geotechnical report, and I'm going to determine a suitable layer. And from that, I can determine the depth. And in some cases, there's some guidance from the geotechnical engineer as well. Good. The factor of safety, you are going to determine that as well, right? That you are going to use or from the code that you are using. Also, the shear, the friction angle, the soil's cohesion, and the unit weight of the soil, you will get that from the soil study. So the geotechnical engineers, your company like Gentech or so, right, to do the investigation, and they would give you those values, right, for the soil in that you're working with, right? And the size of the foundation, 2 meters by 2 meters, right? You as an engineer would actually determine that, right? You may choose 2 meter by 2 meter. You do your calculation, it's not suitable, based on the ultimate beam capacity, and and you need to change that dimension. All right. So here goes. So our ultimate bearing capacity is equal to, let me go to the chart. We have 25 degree for our soil's friction angle. Um, I'm looking for another chart. All right, here it is. Here it is. Modified factors. All right, assuming general shear failure. From this chart, NC would be 20.72, NQ would be equal to 10.66, and um, N gamma, hold on, N gamma will be 10.88. So all the chart I have. All right. Where am I? Will be 10.88. I know that you are seeing some other values here, and I'm going to invite them from a different chart because there are some charts with slightly different values, right? I'll use the chart in this slide, though. Okay. There are some charts, some text with slightly different values. So from there is a matter of plugging in into equation 1.3 times the size cohesion, which is 20, times this, the NC times plus, sorry, these two terms give me Q, good, and times NQ times 0.4 times this gamma size unit weight, good. The foundation is 2 by 2 times the n gamma, and we have 10,078.29 kilonewtons per meter squared, right? And that's the ultimate bearing capacity. And if we look at our the allowable load per unit area of the foundation is QR over Q equal to QU over FS. And so we have 359.5 kilonewtons per meter square. Thus, the allowable gross load is Q equal to 359.5 B squared. Sorry, what are we asked to find? Sorry.
So the allowable gross load.
All right, so our allowable bearing capacity or allowable load is equal to 359.5 kilonewtons per meter squared. Good. Our allowable load is equal to our allowable load per unit area times B squared, and B squared in this case because it is a square foundation, right? If it was a rectangular foundation, it's BL. Good. So it's 3,359.5 times the area of the foundation, which is equal to 1,438 kilonewtons. So if we have a pad this is a pad foundation, right? We are saying that this pad foundation is going to be designed to carry no more than 1,438 kilonewtons. Good? Based on our factor of safety. So if we have a column load and this foundation that exceeded that 1,438 kilonewtons, then we need to change the parameters that we have chosen for our design. Is that clear?
Go for it, sir.
Sir, go over that last part.
All right. If I'm saying if the allowable load, the Q represents our allowable gross load that can be placed on the foundation, and this 2 by 2 foundation, right? With this allowable load for the soil. Good. So it's 1,438 kilonewtons. So say a column was placed on this pad footing, right? And when you calculate the load acting, that is both dead and live load together, right? Acting on this footing, right? This column is imposing. If it's more than 1,438 kilonewtons, then the parameters have to be changed. Maybe you need to increase, for instance, the width of the foundation. Maybe you need to make a 3x3 foundation instead, right? If the load from the column exceeds this 1,438 kilonewtons. Good, this is the allowable load and you cannot exceed it on that particular pad foundation. Okay, guys? Is that clear?
So repeat what you said about the type of foundation, please.
This is a pad foundation, right?
Yes, sir. Yes, sir.
Right. And see a column load, a column is sitting on the pad, which is a normal case, right? And if this column is carrying dead and live load combined, 2,000 kilonewtons, right? Would need to adjust the parameters of this foundation. I may need to increase, for instance, the width of the foundation. Good. Say, for instance, I increase the width of the foundation to 3 meters by 3 meters then, right? Because my column load is much larger than my 1,430. My column load is 2,000. So I increase to 3 meters by 3 meters when I do my design. Times 3. So we have, so it would be that times 9 times 359.5 equal to. So if I increase if I increase my footing to 3 meters by 3 meters instead of 2 by 2, right? Then I'm now able to carry 3,235.5 kilonewtons for the load. So if I have 2,000, no, it would be okay. All right. I'm just showing you if you design a quick what would you what is the next thing that you would do? All right, if it doesn't work. Understand?
Yes, sir. Yes, sir. Yes, sir.
All right. All right. So modifications for water table. So the procedure equation gives the ultimate bearing capacity based on the assumption that the water table is located well below the foundation. However, if the water table is close to the foundation, some modification of the bearing capacity equation will be necessary, right? Okay, so we have several cases. We have case 1, right? We have our water table is actually above our foundation, right? That case 1. We have case 2 where the water table is a distance d below our foundation. Good. So in the first case, the foundation is actually situated in a saturated soil. In the second case, our foundation is situated in dry soil and the water table is some distance d below our foundation. Good. So if the water table is located so that D1 is greater than or equal to 0, but less than or equal to DF. That's where the water table is above the foundation, right? The factor Q in the bearing capacity equation takes the form of the Q equal effective surcharge, which is equal to D1 times gamma, which is the distance from the surface to the water table, good, times gamma, which is unit weight of a soil, plus D2, which is the distance from the top of the water table to the bottom of the foundation, right? Times our saturated unit weight minus the unit weight of water. And you would remember that this term is equal to our effective unit weight. Good? Right? That's Q in this case. Is not straightforward as DF times gamma in this case. All right? So in the first instance, the gamma is the unit weight of the soil above the water table in this area, right? And in the second term, is the effective unit weight of the soil from the water table down to the bottom of the foundation. Also, the value of gamma in the last term of the equation. Also the value of gamma in the last term of the equations have to be replaced by gamma prime, which is the effective unit weight I said before, which is equal to gamma sat minus gamma W. So it's gamma sat is the saturated unit weight, and minus gamma W, which is the unit weight of water. All right. So for a water table located so that D is greater than or equal to 0, but less than or equal to B. So that the distance from the bottom. So for case 2, I'm saying where D, that's the distance from the bottom of the foundation to the water table, some distance down, is greater than or equal to 0. That means the water table does not coincide with the bottom of the foundation, right? But is less than or equal to the breadth of the foundation. That distance down is less than or equal to the breadth of the foundation. Then Q can be taken as gamma dF, right? In this case, the factor gamma in the last term of the bearing capacity equation must be replaced by the factor Q bar is equal to our effective unit weight plus D over B times our unit weight of a soil minus the effective unit weight, right? The proceeded modification are based on the assumption that there is no seepage force in the soil. Good, guys? All right, and case 3, if the water table is located some distance D that is greater than or equal to B, the water will have no effect on the ultimate bearing capacity. Are we clear?
No, sir.
Okay. All right, let me go back. Ready again? All right, case 1 is okay?
I don't understand the part where it's the value of whatever that is in the last term of the equation has to be replaced by that. Does
This
it
one?
mean what does it mean? What does that sentence mean?
All right.
Does it mean that the equation for Q is changed now?
No, let me let me show you. Let me go back to the equation, right? All right. This gamma in the last term, this gamma, right? Good. Becomes this. So we need to calculate all of this to get this value to put into that equation now and replace that term.
Okay, sir.
Clearer now?
Yes, sir.
Okay. All right. Modifications to bearing capacity equation. So the ultimate bearing capacity equation discussed are for continuous square and circular foundations only. They do not address the case of rectangular foundations. Also, the equations do not take into account the shearing resistance along the failure surface in the soil above the bottom of the foundation. The portion of the failure surface marked as GI and GH in the figure. Um, in addition, the load and the foundation may be inclined. To account for these shortcomings, Mayor of 1963 suggested the following forms of the general bearing capacity equation. All right, so we have QU is equal to C prime NC, we know as already, times FC S times FCD times FCI. And these are other bearing capacity factors. FCS is our shape factor for the soil and for the foundation in respect. The shape factor with respect to cohesion. FCD is a depth factor based on the depth of foundation, right? And FCI is the load inclination factor. Remember, normally we see a column coming in vertical, right, and a foundation, but we see many structures nowadays for whether architectural purposes or structural purposes. We have a column that comes in at an angle, for instance, right? And so we have a load comes at an angle. It's a load inclination factor there. Good. And the same for the other two terms. Good. All right, so we have cohesion again. We have effective stress, which we already know from Q. We have soil unit weight, we already know. We have better foundation. And then these are the shape factors. As I said before, these are the depth factors, and these are the load inclination factors, right? And again, we have our bearing capacity factors. Good. Note that the original equation for ultimate bearing capacity is derived only for the plane strain case for continuous foundations, right? The shape, depth, and load inclination factors are empirical factors based on experimental data. All right, so we have some very good formulas here. We have shape factor. Good. FCS is equal to 1 plus B over L, that's the breadth of the foundation, divided by the length of the foundation times NQ over NC. Then our shape factor, QS is FQS is equal to 1 plus B over L times tan of our triangle, and F gamma S is equal to 1 minus 0.4 times B over L. That's for our shape factor. Our load inclination factor is equal to our load inclination factor. We have F gamma D is equal to 1. We have FCI is equal to FQI times, which is equal to 1 minus beta over 90 degrees squared. And F gamma I is equal to 1 minus beta over our triangle, right? At in radians. So that's when F gamma D is equal to 1. So our load inclination, beta is equal to the inclination of load and the foundation with respect to the vertical. We have df over b is greater than or equal, less than or equal to 1. We have our equations, and we have df over b is greater than 1. We have our equations again for our depth, for our depth factors. Good? Okay. We won't go through all the equations. They're there. All right, so we have a square foundation is 2 by 2 in plan. All right, so we have our foundation that we had earlier. Good. And we are asked now to calculate, but now we are going to use our shape factors, our depth factors, and our load inclination factors. Good. Good. So it's now it's a matter class of calculating FS, FQS, and FD, and actually putting them back in this. And put it and just adding them to these to the general form of bearing capacity equation, right? And you should be able to. In this case, we have a bearing capacity of ultimate load carrying capacity of 1,830.8 kilonewtons per meter squared. It's pretty straightforward. It's basically plugging in, calculating the shape factors, depth factors, and inclination factors, and using those in our equation, right? The only thing I need to show you is that the load is vertical. So the inclination factor is going to be equal to 1, right? Good. because it's a vertical loaded on the foundation. All right. Is that okay? All right, a square foundation B times B has to be constructed as shown, assuming gamma is equal to that, saturated unit width is equal to 80.55, or friction angle is equal to 35. The depth of the foundation, I want to place it to 1.2 meters below the ground. D1, which is the depth of the distance between the ground and the water table, is 0.61. The gross allowable load with a factor of safety of 3 is equal to 667.2 kilonewtons, and determine the size of the foundation footing. Good. In this case, the gross allowable load would have been taken from the total load of the building, right? So we divide the total load acting on the foundation, plus with the foundation by 3, the factor of safety, and you'd have gotten 667.2 kilonewtons. And I'm saying this is a load, sorry, multiply it by 3. You'd have multiplied by 3, and I say, okay, this is a load I want to carry for my foundation. And so I need to design a foundation footing to match that load. All right. You understand how I'd get this, right? So I'd multiply the load and the column by 3. All right. And I could actually get this. And then from that now I could calculate my foundation, the size of my foundation.
So you multiply what by what?
Say for instance, I'm working, I want to determine, I'm designing a foundation, and I want to know what size footing I need for this foundation, right? I have all these high parameters, right? To get the load acting down that I'm going to be using, I can also multiply that load by my factor of safety, and that will give me tell me the allowable load that I need to design that foundation to carry. So if I got 200 kilonewtons per meter square, 200 kilonewtons acting on the column, right? Then I want to design and I use a factor of safety of 3. Then I want to design a foundation that's going to actually carry 600. That's what I'm saying.
So it's the dead load and the live load times the factor of safety?
Yeah, so if the dead load and live load is equal to 200 kilonewtons, right? And I'm using a factor of safety of 3. Then I want to design a foundation that can actually carry 600 kilonewtons. Right?
So wouldn't it be the Q allowable times the factor of safety?
It would be the allowable. It would be small q, right?
Yes, small Q allowable.
Yeah.
Okay. Second thing, sir, the factor of safety. How is it determined again?
The factor of safety is in most cases, the practicing engineer will determine based on his uncertainties and all of that, what factor of safety you want to work with. It's normally going to rate between 2.5, 3. All right. Some like pile foundation can go higher, right? But normally it's between that range, right? All right. Or you can use the net increase in your stress as a guide. Good. So if your ultimate load divided by a factor of safety can be equated to your net stress increase in the soil, then you can use that as a guide for to determine a suitable factor of safety. Right? Remember when we did geotechnical, we look at factor of safety, when we look at failure, and we also looked at factor of safety with respect to cohesion, factor of safety with respect to shear. You remember that? Hello?
No, sir, I don't remember.
You don't remember? Okay. But we had looked at factor of safety when we looked at failure in science. We had looked at factor of safety in respect to, and we calculate factor of safety with respect to shear, and also factor of safety with respect to the soil's cohesion, cohesion as against impending failure along the slip plane or the failure plane, right? I'm gonna just pull up that slide next week and just refresh your memory. Okay. All right. So a square foundation. So we have QL is equal to, which is our allowable load carrying capacity of the soil, is equal to our ultimate load divided by our breadth of the or area of the foundation, right? Remember in the first example, we said that QL, that's our ultimate load, was equal to our ultimate load carrying capacity times the area of the foundation. Remember that? Right? Same equation, right? That's rearranged. All right. So QL, which we're trying to find, is equal to 667.2 divided by the area of our foundation. Good. With cohesion equal to 0, for vertical loading, we obtain so since our cohesion was given to be all right, so the cohesion is 0, wasn't stated here, but stake that 0, I'll modify it, I'll add a drawing into this slide as well to show that it's 0. All right. Normally I'll tell you. Okay. So the cohesion of the soil being 0 for vertical loading. So we have no cohesion. So the first term of the equation is omitted. Good. Since the first term is a contribution from the size cohesion and so good. Right? We don't need to use our inclination factors because our loading is also vertical. Good. So QR then becomes QS is equal to 1/3 times our effective stress times NQ times FQS times FQD plus half gamma prime BN gamma times F gamma S times F gamma D. All right, so We are trying to find QL. This equation gives us our original bearing capacity equation gives us QU. And remember, QL is equal to QU over FS. Thus we have 1/3. Our factor of safety was given as 3. For phi is equal to 35. We have NQ equal 29.44. N gamma is equal to 41.06. We are able to calculate FQS 1 plus B over L times tan of phi. We know that, so it's 1 plus tan of 35. B over L, or length over breadth, the squared foundation. B times B that was given, right? Therefore, we know that this term, B over L, is equal to 1. Good? So it's 1 times tan of 34, which is equal to 1.67. Good? Again, F gamma S minus 1 minus 0.4 B over L. Again, B over L is 1. Good? And we have F that's 0.6. So F QD is equal to 1 plus 2 tan of phi angle times 1 minus sine of phi squared times the depth of the foundation over B. Both is given. We don't have B, but we know that the foundation is placed 4 meters down. I need to add that drawing, all right? Which is equal to 1 plus 1.05 B, and our depth factor is equal to 1. All right, so now we can actually add to our bearing capacity equation. Based on where our foundation is located, we are in case 2, so we need to calculate Q differently. No, in case 1, sorry, so it's 15.4 kilonewtons per meter squared. Good. So it's D1 times unit weight times D1 and D2 times the saturated unit weight minus the unit weight of water, and that gives us 15.4 kilonewtons per meter squared. QL is equal to back to our general formula for equation. We have 15 point is 1/3 gamma times our bearing capacity factor in gamma. Then we have our F.
All right, what's going on, you guys?
Gamma
Nick Strength and Power. So
D times 1 plus
from Nick Walker.
0.5 over B, which we calculate as our second bearing capacity factor earlier, FQD.
Now, his caption
right?
on this physique update taken just one day ago was things could get interesting here. And a lot of the comments were wondering and speculating,
Plus
will Nick
half
Walker compete in the Arnold Classic, even though he said
18.5 minus that with effective unit weight times B again times 41.04 times 6, which is our 3 factors.
He was 6th.
Good.
And I think some of these guys
Bearing
like
capacity
Nick,
factor,
hopefully Derek,
depth factor, depth factor, shape factor. Good. And we have equal to, so when we reduce this, we have 252.38 plus 265 divided by B plus 35.89 B. So combining A and B results in a quadratic equation, and we can now solve this equation for B. Good. So the beta of our cage, or the beta of our function in this case, is equal to 1.3 meters. If you're in an exam and you solve 2 year, you'd have gotten most of the marks. Maybe if this question is worth 10, maybe the final answer here I'll give you 2 for it. All right? Because I'm not interested in only mathematics to solve for 1.3. I'm interested that you can get to here and know to solve for B. Okay?
So you're saying 8 marks for the calculations.
Mm-hmm. Yep.
There are 5 reasons why you should not buy the iPhone 14 Pro. Let's go.
Are we good,
On the
everybody?
Genomic Island. Yes, you receive calls, you get notifications, you can access functionalities in certain apps very quickly, but you very quickly realize that
Are we okay?
notification bar. And
So far, sir. So far.
Everybody good? No problems? All right, so just run over that and we'll meet again next week, same time, right?